Okay, so today we are going to wrap up our construction of the tensor product by giving our abelian group that we created in the previous video S module structure. Now, if we recall from last time, given a ring R with unity and two R modules, M and N, which are right and left R modules respectively, we can form an abelian group. This should be. We could form an abelian group called the tensor product, M tensored with N over R, that satisfies the following universal property. So we let iota map the Cartesian product M cross N into our tensor product, be the R-balanced mapping that we defined previously, where we map a pair M comma N into M tensored with N. Then for any abelian group L, an R-balanced map phi, there exists a group homomorphism psi from the tensor product into L, such that the following diagram commutes. So all of this stuff we proved in the previous video, and in this video, what we want to do, we want to look at our tensor product here, and we want to make it into an S module, into an S module for some ring S. Now, to do this, we're going to require the notion of a bi-module, which is what I'm going to motivate right now. So as we said, our question is whether we can turn this abelian group into a left module over some ring S. This, as I said, requires the notion of a bi-module. And to motivate the definition, let's consider the special case of extension of scalars, which I also made a video on. Now, recall in the case of extension of scalars, we are given a ring S and a subring R of S and a left R module N. So we have a module, a left module N over the ring R, and our original question was whether we can extend the action of R on N to an action of S on N. So somehow change the base ring that is compatible in a way that's compatible with our original R module structure. Now, just to review, this is generally not possible in the general case. If we look at the specific case of when we have R is equal to Z, S is equal to Q, and N is equal to Z, so obviously Z is a subring of Q, and Z is a Z module, but we can't make this into a Q module, since this would imply that if we have our 1/2, which is an element of Q, if we have that act on one of our integers, let's say 1, and that's equal to some other integer Z, then we would get this relation here. Z plus Z is equal to 1/2 acting on 1 plus 1/2 acting on 1. From the module axioms, we could distribute the 1 out from the right, because we have this left distribution over these sums in the ring. So we get 1/2 plus 1/2 acting on 1, and then we have 1 acting on 1, and we know that when we have the unity element of a module, the unity element of a ring acting on any element of our module, that acts as the identity morphism. So we get Z plus Z for two integers is equal to 1, which of course is not possible. So that shows that we can't define any kind of modules, any kind of Q module structure on Z. Oh, that shows that we can't extend the Z module structure to Q module structure. But to construct an S module, in the general case, to construct an S module that homomorphically contains N, so we're going to, instead of trying to directly extend the R module structure of N to S module structure, we're going to embed our R module N into an S module homomorphically. And we do this by considering the free abelian group. So that's just the free Z module on the product S cross N, and we quotient out by the subgroup generated by these elements. Now, these are the same elements that we talked about in the previous video and in the extension of scalars video. In the previous video, we were coming at this from the the angle of R balanced maps. In this, we're just trying to generate module structure, S module structure, and these are the module relations that we require for our new object to be an S module. Now we take this quotient, right? So we're going to look at the subgroup generated by all these elements. We're going to call that H, and we look at the quotient, right? So we look at the quotient Fz of S cross N modded out by H, and we know we define that to be the tensor product S tensored with R, tensor over R with N. And this is the same construction that we did in the previous video. And I think we did this in the Scalars video too, but I don't remember. So just to go over it now, we have the same kind of abelian group deal that we have with our, when we look at our tensor product of general tensor product of R modules. And so we want to make this into an S module. And we define the action, right? We define S acting on some sum of simple tensors, since we know that every element of the tensor product can be written as some kind of sum of simple tensors. And we define that action just to be the element S multiplying the first element for each of these simple tensors in the sum. And this is the natural choice for the action. We can't distribute into our second factor like we do in the direct product. Like we have, if we have our direct product, we distribute this into both factors. We have SM, SN, and we can do this here because presumably M and N are both elements of S modules. Here, N is not an S module, so we can't really distribute into that first factor, but we know that S here, of course, is an S module. It's a left S module because all rings are modules over themselves. So this is good. This is a good action, and what we need to do is check that this action is well defined, right? Because if we recall, we're acting on cosets, right? So some of these simple tensors, if we recall, these represent cosets, SOI, N sub I, plus H, right? And cosets can have multiple representatives. And in general, simple tensors have multiple representatives. There's many different representatives for a simple tensor. So what we want to do is check that this action is well defined. And the first thing that we'll note is that multiplying the first factor of the generators of H by any S results in another generator. Okay, so here we're not looking at the action, we're just looking at what happens if we multiply the first element in each of our generator elements. Right, so we have S times S prime multiplied by S1 plus S2, comma N minus S prime S1, comma N minus S prime S2, comma N, right? And this is obviously another generator element, right? Because in this product, we have S prime S1 plus S prime S2, right? And these are obviously elements of S again. So this is obviously in H. We have the same situation here. S prime S, S prime S, and S prime S, right? So this is again an element of H. And then here, this is one of the most important pieces here. When we multiply S prime times S comma R, SR comma N, minus S prime S comma RN. So this is obviously fine. What we can do here though, right, is notice that in this form, this isn't an element of H anymore, or this object isn't one of the elements that we're quotienting out by. But we can see that we can rewrite this through associativity, right? So this is the same as S prime times S times R in our ring S. So this is again is an element of H. So that's important. Then we just suppose we have two different representatives of the same coset. So we have, I'm sorry, not the same coset. We have two different representatives of the same element. So direct sum of, or not a direct sum, just a finite sum of simple tensors, right? So these are finite sums. It shouldn't be the same coset, just the same element. Now we want to act on this through what we just defined, right? So we're gonna we want to show that the action, if we multiply this by s and multiply this by s, that they'll still be equal. So that's what we want to prove, if that equality still holds. But we can realize that if we subtract from both sides, this implies that this element is an element of H, right? Since when we mod out, these are cosets, of course, and if we have two cosets in general, it's equal to BH. That implies that AH minus BH is equal to 0, which implies that A minus B is an H, right? So this implies that this element is an H. And as we know, we saw previously that scaling the first component of elements of H gives us other elements of H, right? So whatever this element is, if we multiply the first component by S prime in each of these terms, each of these summands, and we pass back down to the quotient, we'll just get this is equal to each other. So that's really the same deal. Yeah, so that shows that the action is well defined. But now we want to generalize this to the general tensoring over R with general modules. And the subtle point that we have to point out, the subtle point that we have to make is that in 3, right, in 3 up here, when we looked at this element here and we multiplied by this starred element, this starred operation here, this is the important one, because we use the associativity of multiplication to write S prime times SR is equal to S prime times S times R. And this in general doesn't hold for general modules, right? So I'm just recapping this here. So in 3 we had the element SR n minus SR S comma Rn, and in the quotient we obtained this guy right here. When we looked at multiplying the first component of elements of H by an element of S prime in S, the third condition becomes, right, so we have this associativity condition is very important. And as I say here, we implicitly use the associativity of multiplication in S to write this. This suggests that two things are important for the general case. So the first thing that's important is that in order for us to define the action of a ring S on our abelian group M tensored over R with N, we need M to be a left S module. And in the case of extension of scalars, this was trivial because S is already a left S module. But in this case, we need M to be a left S module so that we can make sense of our action that we want to define, this action. The second thing that we need is in order for this to be well defined, as we showed up here, we need some kind of associativity condition, right? So we must have that the left S module structure, it must be compatible with the right R module structure of M. So that means that, because we know that M, when we have M tensored over R with N, M is a right R module, and N is a left R module. So we want to make M a left S module, but we also want this associativity condition where if we act by S on the product of M, of R acting on M, then we have S acting on M with R acting on S acting on M on the right. I think that makes sense. So we want that associativity condition, and these special modules are given a name. So an abelian group M is called an SR bimodule if it is a left S module, a right R module, and for all S in S, M in M, and R in R, we have that S acting on the M on R acting on M is the same as S acting on M acted on the right by R. So it kind of generalizes the notion of associativity in ring multiplication, where if we look at So if we look at the ring S, right, S is naturally an SS bimodule, right? Since we can act on the left and the right by multiplication, so that's a good property to have, and that shows that in our specific case of extension of scalars, that this bimodule structure is easily satisfied. Now we suppose that M is an SR bimodule, N is a left R module, and we consider the tensor product M tensored over R with N. We define the action of S on M tensored over R with N to be as we defined it in the extension of scalars case. So we have S acting on a finite sum is equal to the finite sum of each of our components being acted, the first components being acted on by S individually. And we want to show that the action is well defined and gives M tensored over R with N left S module structure by way of the universal property that we proved last time. So we're going to use the universal property of R-balanced maps. And how we're going to do this? Well, we're going to define an R-balanced map. So for each fixed S in S, we define the map phi from M cross N into M tensored with N by M comma N maps to, this should be SM tensored with N. Okay, so that's how we're going to define our map. We want to show that this map is R-balanced. So if we're given M1 and M2 in M, we just do some simple calculations. We have phi of M1 plus M2, comma N. That's going to be S times M1 plus M2 tensored with N. And since M is a left S module, we can distribute this into the sum. And then from the properties of the tensor product, and then from the properties of the tensor product, we can factor out, we could pull out these additions, right? These sums. So we have the sum of the two tensors, and that's just going to be what we expect it to be. So that's good. So we're kind of R-balanced in the first factor. We do the same thing for the second factor. Nothing really to report here. It's all pretty much the same. We have M phi of M comma N1 plus N2 is SM tensored with N1 plus, oh my god, what happened here? SM tensored with N2, and then we, oops, no, that's totally not wrong, not right. This is correct, but I kind of want something like this. So that's fine, and then we use the properties of tensor products again, and then we get what we want. We get that the phi is balanced in the second factor. And lastly, this is the important part. This is where the SR bimodule structure comes in. If we have MR comma N, phi of MR comma N becomes SMR tensored with N, right? And we use our bimodule structure here. So this is where we use our bimodule structure to reorder the terms. Then we could pull R through to the other side because we're in the tensor product, and then we get phi of M comma Rn. So we see that phi is R balanced, and by the universal property that we proved last time, and I restated in the beginning of this video, there's a unique group homomorphism, lambda sub s, from the tensor product to itself that makes the following diagram commute. So the important part here is that this is a unique group homomorphism, but it's also well defined. Right, and this shows that the action is well defined. Since this homomorphism is well defined, and this homomorphism represents the action, right? So we know lambda s of M tensored with N is equal to SM tensored with N. And as I said, this action is well defined, the map is well defined, so the action is well defined. And we can write, we know that this here, the sum of these elements is just lambda s of the sum, right? Because lambda s is a group homomorphism. so we can pull this through inside of the sum and act on each component individually. So that's really it. The last thing that we need to do is check that that S module, the S module axioms, right? So we want to check. So the last thing to do is to check that this satisfies the S module axioms, and it's a pretty simple check to show that, and I'll leave that to you to verify, to go through each module axiom and make sure that this does indeed satisfy the axioms.